Opie, you're sitting in the terminal. Gate 22. Coffee in hand. Through the floor-to-ceiling glass. You watch the ramp crews, the fuel trucks, the ground controllers with their orange wands. Everything moving in perfect. Choreographed silence. It looks organized, because it is organized. Down here. But the moment the plane lifts off the runway and punches through the cloud layer, it enters a world with no lanes, no traffic lights, no stop signs. Right now, this very second, there are more than 10,000 commercial aircraft slicing through the upper atmosphere at 900 kilometers per hour. Some of them flying in opposite directions, separated by distances that would make your stomach drop. And here's the thing that should genuinely disturb you. On our highways, with painted lines, speed limits, guardrails, and cameras everywhere, there are thousands of accidents every single day. So how is the sky not a constant rain of falling metal? That question has a real answer, and it's more sophisticated than most people will ever know. Act 1. The invisible floors. It starts with altitude, and the first thing to understand is that planes don't just pick a height and go. There's a system called RVSM, Reduced Vertical Separation Minimum. Decades ago, altimeter technology wasn't precise enough to trust. Aircraft needed massive vertical buffers between them, thousands of feet of empty air just to stay safe. But modern engineering changed everything. Today, the sky is carved into floors of just 1,000 feet apart. But who decides which floor you're on? Simple math. If you're flying eastbound, anywhere between 0 and 179 degrees, you climb to an odd flight level, 31,000 feet, 33,000, $35,000. Flying westbound, 180 to 359 degrees, you take an even level, 32,000 feet, 34,000, 36,000. It's elegant in its simplicity. Two planes flying directly toward each other will always have at least 300 meters of vertical air between them. Not because a controller remembered. Not because a computer checked. Because the rule itself makes it physically impossible for them to occupy the same altitude. It's a passive safety wall, baked into the geometry of flight. Act 2. The invisible roads. But altitude separation is only one dimension. The sky also has roads. They're called airways, invisible highways connecting fixed points in space called waypoints. Every waypoint has a 5-letter identifier. When you open Flight Radar 24 and watch those little plane icons drift across the screen, they're not wandering. They're following routes planned with surgical precision, waypoint to waypoint. Modern aircraft use RNAV, area navigation, combining GPS satellites with inertial reference systems to know their exact position with margins of error measured in meters. Not miles, meters. And horizontally, controllers maintain a standard separation of 5 nautical miles, about 9 kilometers, between aircraft. During final approach to a runway, that compresses to 3 nautical miles. In aviation, predictability is safety. When every plane is exactly where the system says it should be, managing thousands of them at once becomes possible. Act 3. The humans in the loop. Here's where it gets human. The sky isn't just algorithms. It's people, specifically air traffic controllers. And they don't manage all the sky. Nobody does. The airspace is cut into 3-dimensional puzzle pieces called sectors. Each controller owns a specific volume of air. When your flight crosses from one sector into the next, there's an electronic handoff. A digital chain of custody. No plane ever becomes an orphan on radar. The controller's job is to sequence traffic, adjusting speeds and spacing so that a dozen planes all descend on the same airport in a smooth, orderly line. Like threading needles at 900 kilometers per hour. And then there's the language problem. A Japanese pilot, a Brazilian controller. Different cultures, different accents, different native tongues. The solution? Aviation English. Not conversational English. A stripped-down, standardized dialect where every phrase has one meaning and one meaning only. Every clearance gets read back, word for word. The controller transmits. The pilot repeats it back exactly. One error, one misheard number. And the correction happens immediately. Marina 1253, runway 05 left, wind calm. Cleared to land. Cleared to land, runway 05 left. Marina 1253, no ambiguity, no interpretation, just precision. Act 4. The eyes in the sky. Now, how does a controller actually see the aircraft? The old system used primary radar, radio waves bouncing off a metal fuselage, returning a blip on a screen. Functional, but slow. Those radar antennas took several seconds to complete one rotation. A lot can change in several seconds at cruising speed. Today, the standard is ADS-B, Automatic Dependent Surveillance Broadcast. Every equipped aircraft calculates its own GPS position and broadcasts it every second, to ground stations, to other aircraft, to the entire system. Controllers don't see a radar blip that refreshes every few seconds. They see a live, continuous stream of data. Position, heading, altitude, climb rate. All of it in real time. The system doesn't just know where a plane is, it knows where it's going and how fast it's getting there. This transparency is what makes it safe to compress separation distances in congested airspace. Because the data is no longer a guess, it's a fact. Updated every single second. XT5, the North Atlantic problem. And then there's the North Atlantic, the busiest oceanic airspace on the planet. Hundreds of flights crossing daily between North America and Europe. And here's the catch. No radar coverage. None. You're over open ocean. Ground stations can't see you. So how do they manage it? North Atlantic tracks, dynamic airways that are rebuilt every 24 hours based on the jet stream. Those powerful upper atmosphere wind currents that can either slash hours off a flight or add them. Aircraft enter these tracks in precisely timed sequences, separated by strict intervals. They report their position via satellite. It's less like air traffic control and more like conducting an orchestra where the musicians are moving at 900 kilometers per hour and the sheet music changes every day. Act 6, when the system needs a backup. But what happens when congestion reaches its limits? Controllers deploy holdings, oval racetrack patterns in the sky. When an airport is overwhelmed, aircraft don't just circle randomly. They're stacked at different altitudes in a holding pattern, each one on its own protected floor, orbiting patiently until the runway sequence opens up. It's a vertical waiting room. Perfectly organized, perfectly separated. And if a plane loses its radio, loses electrical power entirely, the answer is the aviation industry's most important word: predictability. There's a lost communications protocol. The pilot does exactly one thing, flies the filed flight plan. No improvisation, no guessing, just the plan. And the controller, watching a plane that isn't responding but is perfectly following its route, knows exactly what to do. Clear the airspace ahead of it. Following the rules is how you ask for help when you can't speak. Act 7, the last line of defense. Even with all of this, the altitude rules, the airways, the radar, the controllers, the language protocols, there's still one more layer. TCAS, Traffic Collision Avoidance System. This is the system that doesn't care about humans. At all. It's the most carefully engineered traffic system ever built by human civilization. Invisible, global, running 24 hours a day, trusted with hundreds of thousands of lives every single night. And the reason it works isn't luck. It isn't just technology. It's layers, redundancy. Rules that were written in the aftermath of disasters nobody wanted to repeat. Every time you buckle in and feel that engine roar beneath you, you're sitting inside the product of decades of hard-learned lessons, stacked on top of each other like Swiss cheese slices until the odds of failure become almost mathematically impossible. That's not just engineering. That's civilization doing something, right? Drop a comment below. What part of this system surprised you the most? The North Atlantic tracks? TCAS overriding human controllers? TCAS is a direct conversation between the computers on board two aircraft. No controllers, no ground stations, just two machines detecting a conflict and resolving it in seconds. One plane gets a command, climb. The other gets, descend. And here is one of the most important laws in international aviation. The pilot must obey TCAS before any human controller. If the computer says climb and the controller says descend, the computer wins, always. Because machines process collision geometry faster than any human brain ever could. Act 8, the invisible killer. But the danger isn't just plane versus plane. A fully loaded jumbo jet leaves behind it invisible columns of violently spinning air, wake turbulence. These vortices can roll a smaller aircraft completely upside down, miles behind the source. Controllers account for this too. After a heavy aircraft departs or lands, there are mandatory time buffers before the next aircraft is cleared. The air itself has to settle. It's a layer of protection you can't see, can't measure from the cockpit, and can't negotiate with. You simply respect it. Act 9, the Swiss cheese model. Here's the framework that makes everything make sense. Aviation safety runs on what engineers call the Swiss cheese model. Every protection layer, RVSM. Airways, radar, ADS-B, controllers, standard phraseology, TCAS. Wake turbulence rules is a slice of Swiss cheese. Each slice has holes, individual weaknesses, single points where something could go wrong. But when you stack all the slices together, the holes don't line up. An error that slips through one layer hits the next, and the next, and the next. For a mid-air collision to occur today, you would need the altimeter systems to fail, and the flight plan to be wrong, and the controller to miss it, and the language protocol to break down, and the radar to lose the aircraft, and TCAS to malfunction, all simultaneously. The probability of that chain of failures: 1 in several billion. Close to cinematic finish. The sky looks empty from the ground. It isn't. It's the most carefully engineered traffic system ever built by human. Civilization. Invisible, global, running 24 hours a day. Trusted with hundreds of thousands of lives every single night. And the reason it works isn't luck. It isn't just technology. It's layers. Redundancy. Rules that were written in the aftermath of disasters nobody wanted to repeat. Every time you buckle in and feel that engine roar beneath you, you're sitting inside the product of decades of hard-learned lessons, stacked on top of each other like Swiss cheese slices until the odds of failure become almost mathematically impossible. That's not just engineering. That's civilization doing something. Right. Drop a comment. Below, what part of this system surprised you the most? The North Atlantic tracks? TCAS overriding human controllers? Let me know.